Where mountains touch the clouds and the oceans whisper their call, raindrops begin their humble journey, seeking paths to both edges of the world. From peaks to valleys, from logic to code, we flow through beauty, science, and algorithm alike. Welcome to the Pacific Atlantic water flow problem. Imagine an island represented as a grid of heights. Every cell marks elevation above sea level. The Pacific Ocean touches the island's left and top borders, while the Atlantic Ocean meets the right and bottom edges. Rainwater flows from higher to lower or equal neighboring cells, north, south, east, or west. Our task is to identify all grid coordinates where water can flow to both oceans. In essence, we want to find cells that can drain into the Pacific and the Atlantic simultaneously. Let's look at an example. Given the height matrix shown, we analyze how water flows based on the height difference between cells. From certain cells like 0,4, 1,3, and 2,2 and others, water can reach both the Pacific and Atlantic sides. This happens because there are valid downhill paths connecting them to each ocean boundary. The output lists all such coordinates that satisfy the condition. In the second example, we have a single cell grid. Since this cell is adjacent to both oceans, water can trivially flow to both sides. The result therefore is simply 0,0. This example reinforces that even in minimal cases, the logic of flow remains consistent. The constraints are straightforward. The grid can be as large as 200 by 200, that's 40,000 cells. Each height value ranges from 0 to 100,000. These constraints make brute force approaches inefficient, pushing us to find a more optimal strategy using depth first or breadth first search. Now let's discuss the main idea behind the solution. Instead of checking each cell to see if it can reach both oceans, which would be computationally heavy, we reverse our thinking. We start from the ocean themselves. From the Pacific and Atlantic edges, we explore which cells can flow into them, moving only to higher or equal elevations. Finally, we find the intersection of these two reachable areas. The overlapping cells are exactly those that can reach both oceans. The algorithm uses depth first search or DFS. Starting from each ocean border, we recursively explore neighboring cells that are within bounds, unvisited, and have equal or greater height than the current cell. This simulates the reverse flow where water could have originally come from. Each DFS traversal marks reachable cells in separate Pacific and Atlantic matrices. At the end, we simply check which cells are reachable from both. Here is a simplified version of the C++ implementation. We first declare two visited matrices, one for Pacific, one for Atlantic. We perform DFS from all borders cells adjacent to the Pacific and Atlantic respectively. After filling both matrices, we iterate through all cells. If a cell is marked true in both, it is part of the final result. This systematic exploration ensures full coverage while maintaining efficiency. The DFS helper function handles recursive exploration. It checks all four directions from a cell and proceeds if the neighboring cell's height is greater than or equal to the current one. Each visited cell is marked to prevent redundant computation. This ensures that we never revisit or overflow recursion unnecessarily. The direction array simplifies movement logic and keeps the implementation clean and readable. Let's analyze the performance. The time complexity is big of m cross n because each cell is visited at most twice, once for each ocean. The space complexity is also big of m cross n due to the use of two visited matrices. This is efficient enough for the problem's input limits and balances recursion depth with memory usage efficiently. In summary, water always flows downhill, but our algorithm cleverly climbs uphill from the oceans. We start from the borders, use DFS to mark reachable cells, and finally intersect both visited regions. This approach transforms a seemingly complex simulation problem into an elegant and efficient traversal solution. The Pacific Atlantic water flow problem beautifully merges nature's logic with algorithmic reasoning. And with that, we conclude our journey from rain to river, from mountain to ocean. We have followed the flow of water and the logic of code. Thank you for your attention.